Somewhere beneath your feet, right now, there could be the compressed, unrecognizable remains of a city. Not a metaphorical city, not a poetic one, an actual, functioning industrial civilization, with roads, with agriculture, with waste, with ambition, could have existed on this planet millions of years before the first human ever stood upright. And today, there would be almost no way to prove it happened. Not because the evidence would be hidden, because the evidence would, in almost every sense that matters, no longer exist. That sentence should bother you. It bothers geologists too, when they let themselves sit with it. We are taught, from the first field trip in a school science class, that the Earth keeps a diary, layer by layer, stone by stone. The planet is supposed to be the most honest witness there is, recording every era, every extinction, every rise and fall of life, in a kind of stone archive that never lies and never forgets. That is the comforting picture. It is also, in a very specific and testable way, wrong, or at least far less complete than almost anyone assumes. And in 2018, two serious scientists, not novelists, not conspiracy theorists, a NASA climate scientist and a university astrophysicist, sat down and asked the question nobody in their field wanted to ask out loud. If an industrial civilization had existed on this planet before us, would we even be able to tell? They published their answer in a peer-reviewed astrobiology journal, and the honest parts of their answer are the parts that should keep you up tonight. If this is the kind of question that makes the floor under your certainty feel a little less solid, this is exactly the channel for you. Hit subscribe, and if you've got a guess about what, if anything, of your own life could survive 10 million years in the ground, drop it in the comments before the end of this. You might change your answer by the time we're done. Turn the lights down. We're about to find out how little of the past actually survives, and what that means for how much of the future will survive us. Let's start with the picture almost everyone carries around without ever really examining it. The picture of the fossil record as something close to complete. You've seen the diagrams, a neat, colour-coded column running from the bottom of the page to the top, each band labelled with a period, an epoch, an era. Cambrian, Jurassic, Cretaceous, each one packed with the right fossils in the right order, exactly where 150 years of patient science says they should be. It looks like a book. It reads like a book. Trilobites at the bottom, dinosaurs in the middle, mammals climbing toward the top. Turn a page, descend a layer, and you're reading an earlier chapter of the same continuous story. That story is real, and it is one of the genuine triumphs of human thought. The sequence of life on Earth, confirmed again and again by radiometric dating, by isotopes, by the ordering of strata on every continent, is about as close to an established fact as the physical sciences get. Nobody sane is arguing that the geologic column is fake. That's not where the unease comes from. The unease comes from something quieter, tucked into the footnotes of every geology textbook, something most people walk straight past without noticing. The record has holes in it. Not small holes, not the occasional missing page. In places, the missing sections dwarf the sections that survived. Geologists have a specific, almost bureaucratic word for these holes. They call them unconformities. An unconformity is a surface between two layers of rock where time itself goes missing, where either nothing was ever deposited, or where something was deposited and then simply erased by erosion before the next layer had a chance to settle on top of it. Picture the rock record as a diary that somebody has been keeping for 4.5 billion years. Most days they write a line, some days a whole page, but every so often, without warning, entire chapters get torn out. Not smudged, not faded, physically removed, as if scissored from the binding, and the diary simply continues on the next page, as though nothing had happened in between. You wouldn't know the chapter existed at all, except that the page numbers don't quite match up, and once in a while you find the same missing chapter preserved, intact, in somebody else's diary on the other side of the world. There is one of these tears so large that geologists gave it a name with a kind of grim respect: the Great Unconformity. In places, it swallows staggering amounts of time. Two complete geologic epochs, the Devonian and Silurian, and the youngest part of the Ordovician, are missing, an erasure of almost 100 million years of rock history. One geologist, who has spent a career staring at this exact scar in the rock, put it about as bluntly as a scientist ever does. Geologists might argue about what could have been there, what caused the erasure of the record, but that is all they are doing, arguing. And that particular tear isn't a local curiosity confined to one canyon wall. It is a gap of missing time in the geological record between 100 million and 1 billion years long, and it occurs in different rock sections around the world. 1 billion years gone on multiple continents in a pattern that repeats too consistently to be an accident of one bad afternoon of erosion. And yet, when and how the Great Unconformity came to be is still not totally resolved. Sit with that for a second. This is not a fringe mystery whispered about on the internet. This is one of the largest, best documented gaps in the entire geologic record of planet Earth, discussed openly in peer-reviewed journals, and professional geologists still do not agree on exactly what erased it. File that detail away, we are going to come back to it. Because we don't fully know what erased the billion years of the rock record is not a comfortable sentence to leave sitting on a shelf for very long. For now, notice the shape of the problem we've barely started to open. If a single geological process, mountain building followed by unimaginable stretches of erosion, can strip away a billion years of ordinary planetary history without leaving so much as a scar anyone can fully explain, what exactly are the odds that it would preserve, in loving detail, the delicate, comparatively fragile evidence of something like us? A city is not a mountain range. A highway is not a supercontinent. If the Earth can lose a billion years of its own bones, how confident should we really be that it would keep hold of ours? To understand how we ever got comfortable enough to trust that record in the first place, we have to go back to the people who built our confidence in deep time, and to the exact moment they should have started worrying about its limits, but didn't because they had a bigger fight to win first. The story of how humans learn to read the rocks beneath their feet doesn't start with fossils, it starts with a boat. In the late spring of 1788, a Scottish farmer turned naturalist named James Hutton climbed into a small boat off the coast of Berwickshire with two friends, the mathematician John Playfair and the geologist James Hall. They were hunting for something very specific, a place where you could see, with your own eyes, one layer of rock lying flat on top of another layer standing on end. Hutton had a theory that the accepted age of the Earth, a few thousand years based on scripture, was laughably, impossibly small. He needed proof he could point to. He found it at a rocky headland called Sicker Point, near vertical marine sandstones of early Silurian age, roughly 440 million years old, are overlain unconformably by gently dipping terrestrial sandstones of late Devonian age, roughly 375 million years old. Between those two layers sat a gap of tens of millions of years, a stretch of time long enough for an entire ancient ocean to close, for mountains to rise from its floor, for those mountains to be ground back down to nothing by rain and wind, and then for a new landscape to be built on top of the wreckage, all before the second layer of rock had even started to form. Playfair, standing on that shoreline, wrote down the sentence that every geology student eventually learns by heart. The mind seemed to grow giddy by looking so far into the abyss of time. It's a strange, almost vertiginous phrase for a mathematician to reach for, and it tells you something about what it actually felt like to have your sense of scale broken open in real time, standing on wet rock, watching the ground admit how old it really was. Hutton himself, writing about the implications of what they'd found, produced a line that has outlived almost everything else he ever published. The Earth, he concluded, showed no vestige of a beginning, no prospect of an end. That single unconformity at Sicker Point didn't just extend the age of the Earth, it planted an idea that would define the next 2 centuries of geology, that the rock record is built from cycles of deposition, uplift, and erosion, repeating without any particular reason to ever stop. Which means quietly, right there at the birth of modern geology, the discipline had already discovered that its own archive was full of holes. Hutton wasn't troubled by that, he was thrilled by it. The holes were the proof. The missing time was the evidence of how much time there truly was. For the next 100 years, geologists in the new science of paleontology rode that confidence hard. As rock layers around the world were mapped and correlated, and as more and more fossils were pulled from the ground in a predictable, orderly sequence, the assumption calcified into something close to doctrine. Given enough time and enough digging, the rocks would eventually tell you everything that had ever lived and everything that had ever happened. Charles Darwin, of all people, is the one who first put a very large crack in that assumption, from inside his own theory no less. In On the Origin of Species, in a chapter with an almost apologetic title, Darwin admitted something that should have detonated far louder than it did. Chapter 9 of his book was titled On the Imperfection of the Geological Record, in which Darwin explained that the majority of plants and animals that ever lived are not preserved as fossils at all. He needed the fossil record to show a smooth, gradual parade of transitional forms, walking step by step from one species into the next. It didn't. And rather than abandon his theory, Darwin concluded that the rocks themselves were the unreliable narrator, that the true history of life was far richer and far more continuous than the patchy, gap-riddled sample that had survived to be dug up 100 million years later. He was right to be suspicious. Modern taphonomists scientists who study exactly how, and how rarely, a living thing becomes a fossil have spent decades quantifying just how thin that surviving sample really is. It is often stated in the paleontological literature that the chance an animal will become fossilized is 1 in a million, a figure meant to be taken figuratively, making the point that the odds of surviving the rigors of deep time are extremely remote. Even now, with satellites and databases and global fossil surveys, one recent study modelling which land animals even have a realistic chance of leaving a trace found that nearly 30% of tetrapod species alive today have almost no chance of fossilizing at all, and more stringent criteria for fossilization exclude far more diversity than that. Some researchers estimate the number even more starkly. Across all of Earth's history, less than 1% of species that have ever existed are thought to have been preserved and then actually rediscovered by paleontologists. Think about what that means for a moment, slowly, without rushing past it. Less than 1%. Out of every 100 species that have ever crawled, swum, flown, or grown roots on this planet, 99 are gone so completely that no human will ever hold a single physical trace of them. Not a bone, not an imprint, not a shadow in stone. They lived, they died, and the planet simply closed over the space where they had been, the way water closes over a dropped stone. And that's the fossil record of biological life. Life that, by its very nature, leaves behind hard, mineral-rich, durable parts, shells, teeth, bone, exactly the kind of material built to survive burial and pressure and time. Now hold that number next to a much stranger question. What happens to the fossil record of something that isn't trying to be preserved at all? What happens to a species that builds cities instead of shells? A civilization doesn't grow a skeleton, it grows infrastructure, most of it made of exactly the kinds of material that erosion and chemistry are best at destroying. For most of the history of geology and paleontology, nobody formally asked that second question. It simply never came up as a serious scientific exercise, because nobody seriously entertained the premise. Humans were assumed, almost by default, to be the first and only technological species this planet had ever produced. The confidence wasn't really argued for, it was inherited, the same way you inherit trust in a flaw you've never bothered to test. You don't check whether it holds, because nobody around you has ever fallen through. That is the dead end the question sat in for over 2 centuries. Geologists had proven, beyond argument, that the rock record has enormous, unexplained holes. Paleontologists had proven, with hard numbers, that fossilization of ordinary organic life is astonishingly rare. And yet nobody had connected those 2 established facts into the one question that logically follows from it. If life, this incomplete a record, what would an industrial civilization's record look like? And would we even recognize it if we found it? The pieces were sitting right there, published, peer-reviewed, uncontroversial. Nobody had assembled them into the shape of the thread. That changed, almost casually, in a conversation that started with an entirely different problem. Adam Frank is an astrophysicist at the University of Rochester, who spends a lot of his professional life thinking about the search for life on other planets. Specifically, how you might detect an alien civilization from its effects on the planet's atmosphere, the same way we now watch for oxygen and industrial gases in the atmospheres of distant exoplanets. At some point, Frank found himself wondering about a much closer laboratory, Earth's own deep path. Frank initially reached out to Gavin Schmidt to explore how alien civilizations might be detected through their impact on climate, using tools like ice cores and tree rings, and the two of them soon realized the same idea could be applied to Earth's own history. Schmidt was, and still is, a serious figure in mainstream climate science, the director of the NASA Goddard Institute for Space Studies, not a fringe voice, not a blogger chasing conspiracy clicks. Together, in October of 2017, the two of them submitted a paper to a real, peer-reviewed academic journal, the International Journal of Astrobiology. It was received on the 11th of October 2017, revised in February of 2018, and published that April. Its title asked the question as plainly as a scientific paper ever asks anything. The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? They gave the idea its name almost as a joke, and were careful to say so in the paper itself. They named the hypothesis after a 1970 episode of the British science fiction series Doctor Who, in which a long-buried race of intelligent reptiles called the Silurians are awakened by an experimental nuclear reactor. And they were explicit that they were not suggesting intelligent reptiles actually existed in the Silurian age, nor that experimental nuclear physics was liable to wake anything from hibernation. The name was borrowed for flavor. The math underneath it was not a joke at all. Read that ratio again, slow. 300 years of industry, 400 million years of complex life on land. If you compressed the entire history of complex terrestrial life into a single 24-hour, the whole of human industrial civilization, every steam engine, every satellite, every skyscraper, every war fought over, would occupy roughly the final 16th of a second before midnight, and you'd miss the entire story of us. And from that ratio, Schmidt and Frank drew the conclusion that gives the hypothesis its bite. This short time period raises the obvious question as to whether this could have happened before. They term this the Silurian Hypothesis. Not it definitely happened before, not we have found evidence it happened before, just the plain, unavoidable arithmetic. Industrial civilizations, if they are possible at all, appear to burn brightly and brief, and a brief, bright event buried in 400 million years of geologic time is exactly the kind of thing an incomplete record is built to lose. What made the paper land the way it did inside the scientific community wasn't shock factor. It was the discomfort of realizing nobody had actually done the math. Schmidt and Frank wrote that while much idle speculation and late-night chatter had been devoted to the question, they were unaware of any previous serious treatment of the problem of detectability of prior terrestrial industrial civilizations in the geologic past. And given the growing scientific interest in detecting life on exoplanets, they argued it was worth addressing the question in its proper astrobiological sense. In other words, this had always been a question people joked about over drink. Nobody with a peer-reviewed platform had ever stood up and said, formally, on the record, let's actually check. They were careful, almost defensively careful, to frame what they were and weren't claiming. This wasn't an announcement of a lost civilization. It was closer to a stress test of our own confidence. The purpose of the Silurian hypothesis was never to assert that another civilization actually came before. Rather, it was a thought experiment meant to get scientists thinking rigorously about how we would even know if a pre-human civilization had once existed. A distinction, incidentally, that gets lost almost immediately whenever the idea escapes into the wider Even so, the paper unsettled people in a very specific, very telling. It didn't get dismissed as pseudoscience, because it wasn't pseudoscience. It was methodologically sound, coarse, published through the ordinary channels of peer review. What it did was force working geologists and climate scientists to sit with an uncomfortable Any plausibility the Silurian hypothesis carries stems chiefly from the vast incompleteness of the geologic record, which only gets sparser the further back in time you. The discomfort wasn't about reptile aliens. It was about realizing how much of your own professional certainty was actually built on an assumption nobody had stress tested until. One detail from the paper's aftermath says more about that discomfort than any headline. Schmidt, in interviews afterward, was asked the obvious follow-up question. If you can't trust the rock record on Earth, is there anywhere in the solar system you actually could trust? His answer pointed straight. The moon's going to be there for 5 billion years. That's a long time for somebody to come by and detect, maybe, a strange pattern that we draw on the sun. Notice what that answer quietly concedes. A working NASA climate scientist, when asked where the most trustworthy record of long-dead intelligence might survive, didn't point at Earth at all. He pointed at a dead airlock with no and no plate tectonics. We'll come back to exactly why that answer is so unsettling, and so scientifically defensible, a little. For now, the question the Silurian hypothesis actually forces onto the table is, did it happen? It's much colder than that, and much more answerable. Given everything we know about how rock is made, destroyed, and remade on this planet, how much of Earth's surface has even survived long enough to hold a memory that old in the first place? That question has a hard, physical answer, and the answer is worse than most people expect. Start with the ocean floor, because the ocean floor is where the planet does its most ruthless house. 70% of Earth's surface lies under seawater, and almost none of that seafloor is ancient. New crust is born continuously along mid-ocean ridges, spreading outward like dough pushed from the center of it. And eventually, at the far edges of ocean basins, that same crust plunges back down into the mantle at subduction and is essentially recycled, erased. This planet-wide surface recycling is so efficient that most oceanic crust is less than 200 million years, while continental crust that is billions of years old still exists on Earth's surface. Most oceanic crust is less than 200 million years. Older oceanic crust, denser than continental crust, has long since been recycled in the process of Picture a bakery that never stops. Every few minutes, fresh dough is pushed out onto one end of a long steel. As it's pushed forward, it eventually reaches the far edge, where it's scraped straight back into the mixer, kneaded down, and return to the beginning as raw material. Nothing that ever sat on that table stays there. The table always looks. It is never actually the same dough. That is what 70% of this planet's surface is. Constant. On a timescale most people never think to. In more recent times in Earth's history, basaltic oceanic crust survives at Earth's surface for less than 200 million years before it sinks back into Earth's interior due to the action of plate tectonics, meaning most of the planet's original surface material simply isn't around any longer to be studied directly. 200 million years sounds enormous, until you remember that Schmidt and Frank were specifically interested in the window between roughly 400 million and a handful of million years, the entire span since complex life first colonized. A significant chunk of that window is older than the oldest ocean floor currently in existence. If a hypothetical civilization built anything at all in an era whose ocean floor record has already been swallowed and remitted, there is, quite literally, no seafloor left anywhere on Earth old enough to have kept a record. Not buried too deep to recycled into magma and pushed back out somewhere else as brand new rock, with no memory at all of what it used. Continents fare better, but only in relative terms, and only in scattered fragments. Continental crust is rarely recycled, and is typically much. The oldest recorded rocks on Earth, all located on continental crust in northern Canada and western Australia, date to approximately 3.8 to 4.4 billion years. That sounds reassuring, until you notice the trick hidden in the phrase, the oldest record. Those ancient outcrops are famous specifically because they're exceptions, tiny, precious, geographically isolated surfaces, not a representative sample of what the whole continental surface looked like at any given. Most of the land surface you could actually walk on, dig into, or build a city on top of, anywhere on Earth, is nowhere near that. It has been folded, melted, buried, uplifted, and eroded down again more times than anyone can fully reconstruct. And even where old rock does survive, staying buried is precisely what's, which means the fraction of ancient surface we can actually go and examine directly at the surface right now is small. This is the part of the picture that should really. A civilization's fingerprint doesn't need to be destroyed everywhere on the planet to vanish from the story we tell about that. It only needs to be destroyed or left forever invisible everywhere that anyone has actually. There's a number from one geologist studying exactly this question that captures the scale of the problem better than almost anything else in this whole. Jan Zalasiewicz, a paleontologist at the University of Leicester, who has spent years thinking rigorously about what our own civilization will leave, pointed out something almost embarrassingly obvious once you hear it stated out. Today, less than 3% of Earth's surface is urban, and the chance that any of our great cities would remain over tens of millions of years is vanishing. A city's ultimate fate mostly depends on whether the surrounding surface is subsiding to be locked away and preserved, or rising to be eroded away by rain. And sit with that for it, because it's not about some hypothetical lost civilization. It's about now. Less than 3% of the entire surface of this planet is covered by humans. Every capital, every city, every port and factory town you have ever heard of, compressed into a sliver that, and of the sliver, whether any given piece survives into the deep future isn't a matter of how strong the concrete is, or how many skyscrapers a nation's, or how proud a civilization is of what it is. It comes down to something almost insultingly is the ground under that city, right now, quietly or quietly? That's the whole. Geology doesn't care what, it only cares which way the land happens to. So ask yourself the question this section has been circling the whole time, the one Schmidt and Frank were really asking underneath all the careful academic. Not, did somebody come before? Something closer, something that doesn't need a lost civilization to feel unsettling. What, out of everything you have ever touched, built, loved, or lived by, has any real chance of surviving 10 million years? And not you. Names don't follow. Not you. Houses sit on the wrong kind of ground almost everywhere. Not even, probably, the city you live in, unless the specific patch of crust beneath it happens to be sinking at exactly the right rate, for exactly the wrong reason, at exactly the right moment in geology. Most of what feels permanent to you now, sitting exactly where you are, has already been quietly scheduled for erasure by forces that don't know you exist, and that is not a comfortable place to leave the question. But it turns out the rock beneath our feet may already be holding one clue about exactly this kind of vanishing. a strange, violent spike in the chemistry of the sphere, buried 56 million deep, that keeps drawing the attention of exactly the kind of scientists who know better than to see patterns where it looks, uncomfortably, like something we would and whether that resemblance means anything at all, or anything, is where this gets a great deal harder to look. 56 million years ago, something happened to the chemistry of this entire planet that left a scar geologists can still put their finger on. In a stretch of geologic time called the Paleocene-Eocene Thermal Maximum, global temperatures spiked sharply by somewhere between 5 and 8 degrees, and they stayed that hot for roughly 200,000 years before the planet finally cooled down. The trigger, as far as anyone can tell, was an enormous release of carbon into the atmosphere and enough to leave a permanent signature in rock laid down all over. That signature, the carbon isotope. Carbon comes in slightly different flavors, called isotopes, and one of those flavors, carbon-13, is heavier than the other, carbon. Plants prefer them. So does anything that was once alive, coal, oil, buried organic, which means that whenever a huge amount of ancient, biologically sourced carbon gets dumped into the air, the ratio between those two flavors shifts measurably all over, and that shift gets locked into the rock, forming at that exact moment, like a signature pressed into wet cement before it. Geologists can read that signature 56 million years later, in ocean sediment cores pulled from ore, in ancient soils, in fossils. And when they read it at the boundary marking the start of the Paleocene-Eocene Thermal Maximum, they find exactly the shift expect from a massive pulse of old, organic, isotopically light carbon flooding into the system in a geological. Nobody is certain what. The leading candidates are things like the sudden release of frozen methane from the seafloor, or a huge pulse of volcanic activity injecting carbon dioxide from the North Atlantic igneous. Real, mainstream, actively debated hypotheses, none of them requiring anything resembling it. But here's the detail that makes some research uneasy, in a very specific, very careful, the kind of unease that shows up in cautious phrasing rather than dramatic. The isotopic signature left behind by the Paleocene-Eocene Thermal Maximum looks, in its basic chemical shape, like the isotopic signature we are creating right now by burning coal, oils. Because fossil fuels are, after all, ancient organic carbon, and burning them produces exactly the same kind of lightweight carbon. Schmidt and Frank actually pointed to this event directly in paper, using it as their working example of what humanity's own carbon spike might eventually look like to some futurist, sitting 50 million years from now, staring at a thin, dark line of rock and wondering what could possibly happen. Deliberately, almost pointedly, not to claim the Paleocene-Eocene Thermal Maximum was caused by a lost civilization burning its own fossil. That would be a wild overreach, and nothing in the peer-reviewed literature says it. What they used it for was narrow and, honestly, more a working demonstration that a sudden, planet-altering carbon release from an entirely natural cause produces a chemical signature that a future observer, working only rock, could not distinguish from the isotopes. The resemblance to our own signature. What the resemblance means is complete. That gap between a real pattern and an unresolved cause is exactly where this kind of dread is supposed. And there's a second detail buried in that same event that making our own moment look almost more alarming. The carbon release behind the Paleocene-Eocene Thermal Maximum, as massive was, unfolded over something on the order of thousands to tens of thousands. Human industrial civilization has pushed a comparable jolt of carbon into the atmosphere in a few years. We're not repeating an ancient natural disaster at this. We are compressing a process that once took thousands of years into a handful of humans, which means whatever thin, strange line future geologists eventually find marking our moment, it may be sharper, even harder to explain away as anything. So what, precisely, would that line? If a future scientist, human or otherwise, ever went looking for the fingerprint of an industrial civilization rock, what is actually durable enough? There's a term for exactly this question, coined by the same researcher who pointed out how little of Earth's surface is currently. Jan Zalasiewicz calls them tectonics, the durable, non-biological residues of industrial activity that are physically capable of surviving burial and compression the way a bone or a shell. Not everything we make is, a wooden chair, a cardboard box, paper, cloth, food, mesh. All of it disappears on a timescale of decades, at most degrees, the same as any other organic material, but a narrow, specific category of what we build. It is chemically stubborn in a way nature rarely produces, and that stubbornness is exactly what might let it. Plastic is. Certain plastics are effectively inert, resistant to the microbes and chemical weathering that break down organic, meaning some plastic waste could persist in sediment for hundreds of thousands, possibly millions. Poured concrete, once sets, mineralizes into something closer to an artificial rock than a bill, and vast quantities of it, buried under collapsing structures or swept into river deltas and ocean sediment, would behave geologically much like any other durable, cemented into future sediment. Aluminum too rarely occurs in pure metallic nature, and yet humanity has produced hundreds of millions of it. A pure aluminum object sitting in strata 50 million years from now would be about as natural as finding a photograph. Even biology gets pressed into strange new fossil shapes. Zalasevich and his colleagues have pointed to the domestic broiler chicken as a candidate marker of era, bred over a matter of decades into a body shape and skeletal structure so radically different from any wild bird that its bones would be instantly recognizable in our future as belonging to no natural lineage at all, and its sheer global numbers, tens of billions of individuals processed every single year, make it, body count, arguably the most abundant on the planet in the history of the planet. That's a tale too. A living creature reshaped by industry into something the fossil record has never used before, and probably wouldn't have without us. So the honest answer to the question of what humanity's fingerprint would look like, logically, isn't cities. It's a thin, oddly consistent smear of plastic fragments, concrete rubble, scraps, and abnormal bird bones, distributed globally, all clustered within an almost embarrassingly narrow. And that raises the question under question, the one that circles back to whatever might have. If this is what our fingerprint would look like, buried, pressed, is that the only kind of fingerprint an industrial civilization can give? Ruins, not Jews, not nations, chemistry, and a strange scattering of the wrong kind of rock in the wrong place at wrong depth to have got early. Now put that fingerprint up against the machinery that actually decides whether any fingerprints fall, because this is where the arithmetic turns gentle. Sediment does not accumulate the way most picture it. A steady, gentle snowfall of dust settling year after year into a thick. In most environments on Earth, sedimentation is agonizingly slow, and it is also uneven, arriving in short, violent bursts separated by long stretches where nothing gets to pull. In a typical deep setting, sediment can accumulate at rates of only around 1 centimeter per 1,000. Even in relatively fast depositing environments like river deltas, the long-term average, once you account for every pause and every erosional gap, can work out to only a few centimeters or a few tens of centimeters per 1,000 years, once you smooth the numbers across a large enough stretch of. Picture a single sheet of paper. Now imagine that sheet of paper represents 1,000 years of sediment settling onto. To bury something the size of a modern city under enough rock to protect it from ever being exhumed and away again might take 100 of those. 100,000 years just to get it deep enough to be safe from the surface of slow end. And that assumes deposition stops, never reverses, never gets scraped back off by a shift in ocean currents or a. In reality, deposition instantly. It revertly. Those pauses and reversals are precisely what produce the uncertainties, the torn out chapters we told earlier, the missing intervals that swallow tens of millions of years in a single surface between two. This is the moment those two facts collide, and you can feel the floor drop level. If sediment accumulates in centimeters per 1,000 years, and unconformities routinely erase tens of millions of years of accumulated recordable gap, then any hypothetical industrialization, ours included, would need to get spectacularly, statistically lucky just to end up buried in the tiny fraction of rock that survives long enough to still exist millions later, deposited during exactly the narrow windows when the ground had to be sinking, rising, in exactly the handful of locations on the entire planet, true, at exactly. It isn't that evidence of an industrial civilization would be defined. It's that the raw physical opportunity for that evidence to be observed at all might only ever apply to a sliver of a percent of the surface, for a sliver of a percent of the time. Then think about how much of that already tiny surviving sliver still has to be exposed, discovered, and correctly interpreted by what comes looking, tens of millions. And that thought should sit heavier than it first should. If deposition and erosion are the blunt instruments deciding whether any physical trace is at all, isotopes are the fine instrument geologists to decide, once something has survived, exactly what. And this is where our own moment in history has already, quietly, become a live experiment in exactly the kind of marker Schmidt and Frank. For years now, a working group of geologists has been formally debating whether the Anthropocene, the proposed name for the current human-dominated era of Earth's history, deserves an official spike, a single, precisely dated layer in the rock chosen as the global reference point marking the moment this new epoch began. In 2023, the Anthropocene Working Group formally recommended Crawford Lake in Ontario, Canada as that reference site, and pointed to 1952 as the specific year the new epoch's marker laid down. Chosen because that lake's undisturbed, finely layered sediments preserve an unmistakable spike of radioactive plutonium isotopes, deposited by fallout from nuclear weapons testing that began in the 1940s and escalated through the... Note what that means, plainly, without any... Because this part isn't at all. It's already been measured. Humanity has already created a radioactive isotopic marker so sharp, so globally distributed, and so chemically unlike anything produced by natural processes that scientists have chosen it as the literal boundary stone of a new Plutonium-239 barely exists here at all. Its presence, worldwide, in a thin band of sediment is artificial, entirely recent, and entirely ambiguous to anyone who knows. Which raises the obvious, uncomfortable question nobody in this video answered, because as far as the published literature shows, almost nobody has systematically. If a plutonium spike, or something like it, is exactly the kind of marker an advanced industrial civilization behind, sharp, artificial, globally synchronized, chemically impossible to explain through geology, has anyone gone back through the strata, the Paleocene, Eocene, the Mesozoic, specifically hunting for an anomaly, at a resolution, anywhere else in? The honest answer at this point is not, no, not. The honest answer closer to, really, not at the resolution it would acquire. Schmidt and Frank said themselves, the search they were calling for was, at the time they wrote the paper, still more. Nobody has done the exhaustive isotopic sweep of deep time that would actually be required to say, with confidence, that no other spike like ours. The absence of evidence, in the particular case, is disturbingly close to the absence of anyone having. So if Earth itself is this bad in records, this eager to erase, this selective in what it preserves, this unsearched in the corners where the answer might be sitting, is there anywhere in the solar system that Dublin? Somewhere without oceans swallowing floor, rain, without tectonic plates constantly folding the evidence? There is, and it's been sitting in plain sight the entire time, close enough to see with your own eyes on at night. The moon plate tectonics, liquid water, and vertical atmosphere, which means it has almost none of the machinery that destroys Earth. There is no wind to sandblast a foot into nothing. There is no rain to dissolve the edges. There is no ocean floor sliding into the induction zone, dragging the evidence down into the mantle to be melted and rebuilt. The footprints astronauts left on the lunar surface during the Apollo missions are expected to remain largely intact for millions of years, since there is no wind or water erosion on them. The primary threat to that record isn't at all. It's the slow, random bombardment of micrometeorites, striking the surface over and over across deep time, which will eventually blur and erase even undistant terrain. But that process operates on timescales of millions of years, not centuries, which puts it in an entirely different category of durability than anything else. That is precisely the point Gavin Schmidt was making when he said the moon would still be there in 5 billion years, waiting for someone to notice a strange pattern in dust. He was being poetic. He was making an actual technical comparison, pointing out that the most reliable archive of intelligent activity anywhere near Earth might not be at all. It might be sitting completely undisturbed, 1/4 million miles away, in a place with no weather, no oceans, and no plates to the evidence. Mars complicates that picture in an interesting way, because Mars occupies a strange middle ground between Earth's ruthless recycling and the Moon's nearness. Mars has no plate tectonics in the Earth-like sense, and no active mountain building recycling its crust Earth's does, which is part of why some of its geologic features, like the volcano Olympus Mons, have been able to grow for billions of years without ever being torn down. But Mars is not still. It has thin winds capable of raising planet-wide dust storms, and evidence of ancient water that once carved channels and filled basins across its surface, long before the planet dried into the desert world today. Which means Mars would preserve some ancient markers extraordinarily well, sealed under dust for eons, and simultaneously erase others, slowly, unevenly, the way a desert buries a road it meant to keep. None of this proves anything sitting on the Moon or under the Mars. Nobody has found a technofossil in the world. No mission has ever gone looking for one, because no mission has reason to. But the mere fact that both places exist, both physically capable of preserving exactly the kind of evidence Earth is so averse to destroying, turns an abstract thought experiment into something with an actual shape. If there ever were an older industrial event in this system's history, and that remains a genuinely open question, not a claim, the Moon and Mars are, quite literally, better witnesses than the planet, which leaves you standing in a strange, specific place. Earth, the world we assume remember everything, turns out to be one of the worst possible places to leave a permanent record at all. While two completely dead worlds, one of them close enough to touch a telescope, sit quietly preserving what we've been handed, indifferent, patient. And if that theory is real, if the planet best suited to producing intelligence is also one of the worst remembering it, then the silence in Earth's own deep past stops her. It starts looking like exactly what you expect to find, whether or not something happens. And the same asymmetry, quietly, applies to us too now. To every fingerprint we are real time, whether or not anyone is ever around. Sit with that asymmetry for a moment, because underneath it is a conclusion so simple it barely argued for. It just needs to be said out loud, plainly, without any drama. If an industrial civilization existed on this planet millions of years before us, built a version of cities, burned a version of fuel, altered its version of the atmosphere, and then declined, or died, please stopped, the physical processes we've just walked through mean we would very likely never of it. Not because we looked hard enough, because the planet itself does not keep. And the second half of that sentence is the one that really land, because it doesn't stay in the past, it points. Whatever we build, whatever we bury, whatever isotope we scatter into the rock right now, in this century, is subject to exact machinery, same erosion, abduction, the same odds, measured in centimeters per 1,000 years, of ever ending up in the tiny sliver of ground that survives to be found. We are not exempt from the process we've just spent describing. We are, right now, subject. That is the telling implication. And notice that it didn't require a single unproven arrive at. It isn't a prophecy, symmetry. The same physical honesty that makes it plausible we could have missed a civilization is the same physical honesty that makes it plausible future observer, whoever or whatever turns out to be, us. Now, before that symmetry hardens into something heavier than the evidence actually supports, it deserves to be interrogated the way any serious hypothesis is interrogated. Because the honest version of this story isn't, we first. The honest one is narrower, stranger, and it comes with real limits that Schmidt and Frank themselves were careful to spin in their own paper. Start with the caveat as most. Absence of evidence is not absence, but it is also not presence. Nowhere in the peer-reviewed literature does anyone claim to find a technofossil, an anomalous isotopic spike, or any other physical marker suggesting a prior industrial civilization existed. The Silurian Hypothesis is discovery, methodology, a way of asking whether our current search techniques would even be capable of detecting such there. Schmidt and Frank's own conclusion was measured almost with caution. They were not arguing that a prioritization occurred, only that if it had, our current geological and paleological toolkit might not be sensitive enough completely. That is a very different claim than the internet often turns it into. There are also real physical reasons the array not be total. Some geological environments are simply than others. Deep marine sediments in tectonically stable basins, certain ancient lake beds, and specific continental interiors that have avoided major mountain building or glaciation for millions of years do preserve unusually long fields. Not everywhere on Earth has been equally. If a hypothetical event happened to leave a signature in exactly one of those red stable pockets, it's not impossible that a sufficiently careful search find it. Odds are poor, 0. And the difference between poor and 0 is where on it. There's a sin limit worth naming, because it cuts against the dread rather than deepening it, and a script that only ever climbs is neither. Geologists are, in fact, actively getting better at reading exactly the kind of faint signal this hypothesis depends on. Isotope geochemistry has advanced enormously in the last 2 decades. Techniques that can detect the faintest chemical fingerprints of ancient volcanic events, ancient impacts, ancient climate shocks, at resolutions that would have been impossible ago. If Schmidt and Frank's paper does what they hoped it would do, and pushes even a handful of researchers to run the isotopic sweep of deep time has yet run, that gap in the search itself goes. The hypothesis is not a door. It's closer to a door nobody has bothered to check. So the fair, fully honest position is specific. The Silurian Hypothesis is a real, published, peer-reviewed thought experiment, built on facts disputes. The income of the rock record, the brevity of industrial civilization's deep time, the genuine difficulty of distinguishing a natural carbon spike from an artificial one. It is not proof of civilization. It is proof that our confidence in ruling one out was never. Those are 2 very different sentences, and the second one is the one that fact-check. It is also, somehow, the more disturbing of the 2, resolve. It just tells you they'll open. And once you let that question stay open, it stops into Earth. It's reaching outward, toward a much older, larger silence that scientists have been staring at with growing unease. In 1950, the physicist Enrico Fermi, sitting at lunch with colleagues at Los Alamos, is said to have asked a question that has haunted me ever since, in a formula as simple as, given how many planets there are. The galaxy is old, it is enormous. It contains hundreds of billions of stars with planets, some of those planets sitting in exactly the temperate zone where liquid water and possibly exist. If intelligent, technological life is even moderately likely to arise when conditions allow it, the galaxy should, by now, some sign of it, a signal, a structure, a footprint of somewhere. Instead, when we point instruments at the sky, we get nothing. No radio that isn't natural, no structure, no confirmed trace of technology anywhere beyond this small planet. That contradiction between how likely intelligence seems on paper and how silent this actually is what's known as the Fermi paradox. One of the proposed explanations for that silence is a concept filter. The idea that somewhere along the long chain of steps between lifeless chemistry and a civilization capable of being detected across stellar distances, there sits some barrier so difficult to pass that almost through it. Maybe the filter is early, in the jump from simple chemistry itself. Maybe it's in the jump from single cells to complex multi-organisms. Or maybe, and this is the version that connects directly back to everything we've just been walking through, the filter isn't about whether civilized at all. Maybe it's how long they last, and how loudly they announce themselves. But that reframes the silence of the universe into something muchness. It isn't necessarily alone in space. It's that intelligence, wherever it arises, may be strictly alone in time, separated from every other instance of itself not by distance, which telescopes could someday close, but by tens of thousands or millions of years of cosmics on either side, which nothing's ever. Because that gap isn't a distance, it's a direct travel in. An Earth's own record, or the almost complete absence of one, is a small, local demonstration of exactly why that's so total. If we cannot even reliably detect whether a civilization rose and fell on our own planet, in our own rock, with our own feet, then the odds of ever detecting one that rose and fell on a planet 4,000 light years away whose signals stopped broadcasting before our own solar system had even finished forming its ocean, not small, close to none. Not because such civilization never existed, because it, briefly, then falling silent, might be the single most common outcome for intelligence where it arises, and silence, once it sets in, may be permanent in that matters, everywhere, always. That is the point where this stops being only about geology, about the galaxy, and folds back down to something you feel personally, standing wherever you happen right now. Because if intelligence is this brief, this rare in the time of a single planet, and this quiet in the timeless as a whole, then you exist at all, in a body capable of asking these questions, during the one narrow slice of history when a species on this planet and to be technologically curious and at the same time is not for granted. Complex life has had 400 million years to live on Earth alone. Out of all of that time, the window in which a mind that can look up the age of a star and wonder whether it is the ever has, might only ever open for a to stretch. You are standing inside that now, so ever loved, so will close. But right now, for reasons that owe less to destiny than to all bearable luck, happens to be open, and you happen to be behind it. That luck, though, buys you numbs after, never has. Guarantees no no memory, no pick in any future rock explaining who you were. The same brute physical honesty that makes it possible we miss earlier civilization is the same that makes it certain, not probable, certain, that most of what defines your life, right down to that it happened at all, will not survive in any form and will ever read. That isn't a sporty aimed at you. It's the ordinary, indifferent operating condition of being alive on a planet that has never once, in 4.5 billion years, go back one last time to that quiet, half-joking name a NASA scientist and an astrophysicist gave in thought experiment, borrowed from a decades-old television episode about a buried civilization find. The real subject of their paper was never a lost race of reptiles, Silurian rock. It was a mirror, angled just carefully enough, looked at it the right way, you'd event yourself. The honest answer to whether something like us, for us, is, remain forever, we don't know, and will never be able to know. But our more immediate answer, the one that doesn't require finding anyone else at all, is sitting in the ground beneath every earth right now, waiting to find out whether the rock beneath it happens to be sinking. Somewhere, tens of millions of years from now, if anything is left standing on this planet capable of questions at all, it may dig down into the crust beneath whatever ruins are left of your world, as nothing. A thin, strange band of plastic fragments, an odd ice where none should be, a few bones from a chicken, shaped by nothing evolution on its own. And it will have to decide, the same way we now have to decide deep past behind us, whether that thin band means a civilization rose and vanished at all. It will not know for certain either way, and you, right now, reading these words in the one brief window when a mind on this planet had be awake enough to ask, lies. If this changed the way you think about the ground under your own feet, that's exactly what it exists to do. So subscribe. Go, tell us this. What do you think survives of your life a million years from now? Survives at all?